Okay, so today we have two topics. Scott is going to present some exciting results on inhibition of return and saliency-based policies, motor-free policies. And the results are really like sparser models and using less steps and better accuracy, so they're good on every front. And then for the next topic, Jeff's going to present ideas on locations, how they can be represented in the column, and how that could help for voting and representation of location in general. This is a topic that we've been coming to for a while, so it'd be good to get some clarity on. I guess Jeff, your topic is more.
I didn't promise clarity. I just promised a
Well,
discussion.
with more discussions, we'll get clarity. Your topic is more like open-ended discussions, so maybe if you don't mind, we could start with Scott's topic.
No, sounds exciting. Sounds great.
Cool. Go ahead, Scott.
All right, so what's the best sequence here for the share? Step one, goes over here. Boom, boom. We had this all worked out for that one thing we did. Okay, you guys are seeing...
We're seeing the presenter mode, unfortunately.
Okay. Let's try...
Yes.
Okay. Okay. So just a quick background, or just like we've got new people on the team. So, I've been working on this thing for a while, 6 or 8 months or something like that, about how to get our distant agent to move around a little bit smarter and a little bit better. And we've got it. When I say move around, I mean eye motions, not walking or anything like that. But we want our distant agent to sort of move its eyes around like an animal would. Attend to things that are interesting in an image, ignore things that are less interesting or less distinguishing. But when I started on this project, what we had for the distant agent was this kind of policy on the left, which is a scan. It's essentially, you can see just kind of just doing this outward spiral scan, and it works well for getting good object coverage, but it's not exactly biological. It also kind of, it's a uniform treatment of the object surface as a whole. So the idea was like, can we move away from this and come up with a way to explore just the most distinguishing or informative features of an object? And then that way, we should be able to get sparser models as well, because we don't need to densely represent every single... You have a flat board, Monty is just going to remember every single little piece of that board, at that point. And this is the surface agent just for reference, because we are going to be showing some results with this as the backbone. And then the inference policy, I just lifted this from Wikipedia or something because I didn't have time to make a nice image of what the actual random walk was. But essentially, Monty its eyes would land upon an object, and it would just kind of start doing this random walk. And it's pretty good at exploring local areas. It's a fine policy if you want to explore locally. But it is less than optimal for recognizing objects for the reason that you may not get to the part of an object that really distinguishes it for quite a while. You could be randomly walking around some patch of a cup, for example, and you've got 10 cups that look just like it, and you want to be able to go to the place that's going to help you distinguish between these objects. So that's one aim of this. And sort of tied to that, was this idea that we've got these pretty dense models. They can get pretty big, 4,000, 5,000 points big. That's pretty. It can slow things down for us, first of all, because each one of those becomes a hypothesis. We got to do hypothesis testing. You've got 77 or hundreds or more objects. You can cut those models down in size. It's going to make inference much more feasible. So the idea, this goes hand in hand with what we were talking about, which is maybe I don't really need to memorize everything about this object. I just need to memorize the parts of it that seem really salient. And during inference, I can come back to it. I can kind of also tend to the same basic regions because they're going to be salient also during inference. And that should push me towards visiting areas that I have learned pretty well and kind of ignoring areas that may not be as interesting. You can see here, we'll have a closer look at all these models, but that's a boundary on the label. And we got a nice red, it's like a perfect yellow-blue opponency situation going there. So, yes. So I think are there any questions on that so far before I move on? Am I going too fast? We're good?
No, it's great. And yeah, I guess maybe just for some additional context with the sparsity. So I guess at a high level, we like you mentioned, Scott, it's computationally efficient. But also like that means that it's going to eventually become a blocker to a lot of the things we want to do, like object behaviors and scale invariance and these various things that are going to increase the dimensionality of our representations. And so right now, this kind of naive approach of having these like super dense models, it is going to break down at some point. So it's not just like conceptually, it's going to become important that we have kind of sparsity for those reasons. And yeah, and although there's other elements that we'll need for sparsity in terms of kind of like how we actually represent the model and things like that, this is definitely a key part of that is these more intelligent policies.
Thank you. Yeah, I've been kind of shying away from talking about policy because this is also a sensor module, but it goes in hand. I think we had talked in a previous meeting where Tristan and I presented what we have been up to. And so this Salience sensor module, it has to work with the motor system also. So it's sort of like a policy, but sensor module sort of combined thing. So I don't really have sometimes I use the word mode because it's kind of a policy plus motor system configuration kind of thing. But
yeah, you mean the terminology around that? I guess more strictly, we might call this like a goal generator rather than a policy in the sensor module.
Right. Policies on the motor system side. All right, so that's where visual salience is kind of like a first idea, best idea. It kind of makes a lot of sense. You're going to want to attend to the interesting parts of an object. It's pretty intuitive. There's tons of research on visual saliency, both experimental and theoretical, and there's a bit open source code. There's a lot of theory. One of the cons, though, and we don't have to get into this in too many details, but there's no guarantee that visually salient features will be the most informative with respect to object recognition, for example. Does that make sense? I mean, if you had an object data set and they all had the same kind of salient type feature, like a car, like if you had a bunch of cars, maybe there's spots on cars that are quite visually salient and you keep attending to them, but it's actually like, I don't know, the license plate or something like that. It's kind of a bad example because that's model based. The point is,
I saw this on the spam can picture earlier. So you made a distinction between the yellow and the blue areas, but but I was actually attending to some of the words and some of the, iconography on that, which is maybe model based, but the point is that the things that really help me understand what this can is are not necessarily the big blue and yellow line distinction.
Right.
That may be, but it may be a bunch of cans that are like that, and it's the words and the other things that make a difference. So I was thinking of that too, like, oh, look at the details of the little circle there. That doesn't show up on this your saliency map on the bottom right. Um, it doesn't show up too well, at least. Anyway, I'm agreeing with you. I think there's some downsides to just picking the obvious saliency points.
Right. Yeah, I think we kind of want to bootstrap uh, the learning module side. Like the saliency kind of stuff should be a way to get our learning modules more quickly um, to control the system. So we're really just
Mm.
talking about getting the first handful of steps going. Maybe it helps during exploration and learning, but
So what, then you'd switch to
um,
more model-based quickly as you could? Is that the idea?
yeah, it does that automatically now. The way that we reconfigured everything is that anything that comes from a learning module is going to be prioritized. It's just going to do that. But in the absence of that, the motor system will enact the goals that are coming out of the sensor module, the salient sensor module. So it's kind of a natural handoff. Like basically, as soon as the learning modules feel confident enough to present you with an option, you will take it. But we're hoping to shorten the time frame that it takes for them to get to that point where they start submitting requests. One other thing that was kind of tricky here was there's not a ton of parameters, but changing a couple parameters like the center surround, smoothing kernels, and if you change the viewfinder resolution, that kind of changes things too. And so there's a bit of a slow um, it's a bit of a slow process because you also want to come up with something pretty general. Like you don't want unless you've got some way to adaptively tune your parameters. It's not like we want to set the parameter for one kind of experiment with this value and this for another one. So it can take a while to sort of tinker with and figure out what's going to work. But the approach that I ended up landing on is called VOCUS 2. We have talked about Eddie Koch's model before. This is basically a revisitation of that with some adjustments that help with spatial scale invariance and sort of better tiling the scale space. Eddie Koch was 2000, I think, and this paper came out in 2015. This is an example from their website. Input and salience, it looks pretty nice. It captures, I think, for the most part, the features you want to attend to. But the main idea behind it is that you've got luminance, red-green opponency, blue-yellow opponency. We added the depth salience. That's kind of our extension to the system. There's orientation salience. So you just basically just compute a bunch of different salience maps, and you find a way to normalize them and add them together to get some aggregate or some collective map of areas you might want to attend to the most. I mean, it looks here like that's pretty hot, that corner of the label. Right there too. So I also wanted to give a shout out to the authors because they do quite a bit of cool stuff. You can check out their lab here. Whoop. And this is the paper that's just unfortunately paywalled, but the paper that presented VOCUS 2. And
It's interesting. You pointed out that the real highlight at the top of the right below the, I don't know, we were just pointing at it, up here.
where
Uh, um,
Yeah,
right,
sort of like the
that
top of the mustard bottle, but before you
right,
get to the lid.
right. That's really a reflectance thing, and it's really not. It's not really a salient part of the physical object. It's in that case,
Yeah.
it's something you really would rather not have in some sense. You know what I'm saying? Um,
Hmm.
anyway,
Yeah,
so that's a kind of
yeah,
in different lighting conditions that wouldn't be salient at all.
Right.
yeah, and it is kind of interesting. Um, I think, for anyone watching this, it may be worth mentioning that the 80 Coke is kind of a biologically inspired um, kind of saliency system, and obviously this builds on this. So, in theory, it's kind of trying to capture what some believe kind of the early visual system is doing, but clearly it is a simplification, as you say, Jeff. Like if we
Well, I'm
had
not saying.
access to the saliency maps that humans, I mean, at least I could imagine that there are ways that we kind of filter some of this, and it is a bit
Well, right. Well, I think I'm putting a model-based interpretation on this,
right.
which
That's
is
that's
they
definitely part of it, right?
right,
But like
right.
you were talking
Whereas
about the other day, that like I think with like shadows, that
right,
those are like a dark edge on a light background.
right.
But it feels like, at least even in a model free way, we don't really attend that much to shadows.
Well, it's
Um,
so hard to know because we're not really
right.
the our subjective experience is all model based. And so we can't really know what's going on subcortically elsewhere, you know. So it may be that the superior colliculus or whoever is providing this is like, hey, that's a really salient area there, the shadow or this highlighted limb. But in the end, the model itself says, no, that's not an important, that's not super important. That just happens to be reflected light. So that's an interesting challenge, you know. But I
Yeah.
assume from a model free point of view, I can't object to it. They were like, what else can you go on, right? There's a high contrast area, there's a lot of curvature. You know, anyway, I guess it's interesting just to think about it from an introspection point of view that, I can say, oh, that's not important, but how would the subcortex know that? It probably wouldn't. It'd have to do what Scott's doing. So,
Yeah, I'd like to read more about that. Discounting the luminance. I only remember the term because it came up in a class and we did a bunch of stuff on it, modeling with it. I'm not really sure how we would incorporate it, but something along those lines. It's not really the same though as like knowing where a light source is. It's more
well,
like
no, but I mean, all you're doing right now, right, is trying to direct where to learn, and maybe beginning where to infer. But we'd have to assume that somehow the ultimate model, if I learn this in different lighting conditions, the model wouldn't be focused on that particular area because,
right.
right, in different situations. So, it's sort of bootstrapping as you described it, Scott, right? You're like, okay, where do I start for learning? Where do I start for inference? And it's kind of hard to argue against it. But once you have the model going, you can say that's not an important area, you know.
Hmm.
Um,
Yeah, there was a paper from February this year. I haven't read it in detail, but the general gist of it was that elements of visual attention in the superior colliculus are learned as well. Um,
mm,
and so you could imagine maybe superior colliculus is learning like simple sort of model-free pattern detection type things that go a little bit beyond some of these things, like I don't know,
mm,
for example, and it specifically they talk about learning based on behavioral relevance. So I don't know, maybe for a human, we look at
right.
so much text over time, we have this sort of like just coarse text detector that sort of picks that up and in a sort of model-free way. Um, and so that could be
Interesting.
part of kind of
Or a crude model way, I guess you could call it, right? It's if it's
yeah,
learned,
like more kind of like a fixed template matching thing rather than
right, right.
a structured reference frame that you path integrate
Yeah,
through.
yeah.
Model light, maybe.
That's good.
I'd be curious to take a look at that. I'm just here, interested in how they can determine that the learning what's happening there rather than like feedback from visual cortex or something. Maybe it's a timing thing.
That's
If it happens
yeah,
early enough, then maybe they just assume that it's couldn't have come from cortex.
yeah, it's a great question. Yeah, I can't claim to have read the paper to answer that, but I've just shared it in the
Mhm.
chat for anyone who's interested.
Okay, thank you. I think we can move on to the results here. So last week, I decided to push the sparsity thing to see how far we could take it. At what point does it kind of break down? Because we were seeing some nice early results that we could get pretty sparse models and have pretty good performance, both accuracy and efficiency. So this is just to show you what they look like. This is the model that was trained using the surface agent. And our benchmarks use this guy right here. Pretty dense, 2,300 points. This is about the same density here. You get 500 points. You can tell they're mostly clustered though, so we could sparsify that by not allowing points that are so close to be stored.
Wait, those the points are more like 2,500, right? That's the number of steps in the experiment.
Points. Okay, sorry. It's the number of training steps that was given per episode here.
Yes, yeah, it's like 500. But okay.
All in all, the model got 2,400. I really just dropped it down because I wanted to give our, as I was writing our negative results report, I was like, well, at least I'll give it a fair shot, against. I'll try to balance the model sizes so that, this model is about the same size as the VOCUS one. And then that's when the good results started happening. So this VOCUS 125 here, I'm just gonna be kind of referring to that as the sweet spot. Sorry, Nils, I didn't get a chance to get to the violin plot. So this is what we have.
No worries.
These are the distributions. This charcoal line here it's a bit funny because it's quite squashed to get them all on the same page, but it's got fat tails. It's got some really big models, some really small models. It's kind of all over the place. I think the median's around 2,000, 1,800, something like that. That first dense VOCUS model I trained was definitely bigger. You can see this darker line. And then push it a little bit further and your models not only get sparser, but it's kind of nice that they're narrowing so that our models naturally are all going to be roughly in the same neighborhood, not as wide of distribution, but which I think is quite nice.
And the reason with the current baseline models that they have such a large distribution is because in YSV dataset we have quite small objects like a dice and then much larger objects. And so the much larger objects will have a lot more points versus here you'll saccade to the same amount of salient points either way. So even though the object sizes are different, you can get similar amount of points, which is nice.
I didn't talk about the inhibition of return, but we covered in a previous meeting, but maybe I'll just mention for other viewers that that's a necessary component of this, of saliency driven saccades, because you need to stop returning in the same areas. And that's another set of parameters you can play with. Like if you want to keep driving exploration to prevent returning to the same areas, you can like push that out or simplify it. But yeah, okay. Moving on, we might as well take a look at the inference. So because these plots are a little funny to look at, I just wanted to make a little like diagram of what they're going to look like. So this charcoal one, this is our benchmark going back like a couple months ago. This green one.
Percent correct, or what would be the y-axis?
They'll all have y-axes, but I just wanted to show what the
structure.
What is the y-axis?
The y-axes will be different things, but because I thought this was kind of confusing to look at, I figured I would make a little helper diagram here to kind of explain what the structure of these diagrams is, which is basically that one on the left there is our benchmark from a couple months ago. The green one is from when Tristan and I merged the Salience SM that had uniform salience, so it's just inhibition return. and the lookat policy. And then all these blue ones here, that's VOCUS. We're training models using VOCUS and performing inference, and they're just getting sparser and sparser. And that little star there is my sweet spot, so you can keep an eye on that. So here's accuracy. We had a nice jump in accuracy when we switched to that inhibition of return. What I'm showing here is like, I just wanted to change the Y limits because it's just too hard to look at here. So this is going from 75 to 100. And then, we pretty much recovered like these sparse 2, these models are about half as big as this one, IOR on surf, the surface models. Like that's a huge drop in number of points per object, and maintaining almost the same level of accuracy. Some experiments are better, some experiments are worse. They're kind of neck and neck. It's not like they're uniformly worse.
Yeah, and I mean that difference in accuracy, that's like within the normal variance that we see. Like it's not like it's necessarily worse. It could just be a random variation.
Yeah.
If there's a
Different seed.
1% point difference.
And there's kind of two sort of challenges to using these sparse models that are maybe worth emphasizing, which is one is these objects are being presented at random rotations. So it's not kind of trivial to just return to the same kind of regions on the objects that you visited during learning. Somehow the kind of salience policy needs to be kind of robust to that. And then the second thing is what is picked up by the salience policy and what is kind of stored in the model needs to be, it's sparser, but it still needs to be sufficient to distinguish the objects. Because you could imagine kind of like a degenerate solution where like, okay, there's one salient point and we always attend to that. But that's not going to distinguish these 77 objects that are very similar along many different dimensions. And so the fact that this is able to kind of seems to identify that kind of minimal but sufficient and necessary set of kind of features or regions to focus on to still distinguish the objects, but with far fewer points. Yeah, that's pretty encouraging.
I just started thinking about like two different basketballs. Imagine a basketball is pretty much featureless. It's not really, but it's two basketballs. They're going to be pretty much the same, except for the logo. I think if I were to try to memorize one basketball versus another, I'm definitely focusing on the logo, and definitely. Oh, okay, but never mind. That's an aside. I'm going to get to efficiency before I derail myself. So here's the number of Monty matching steps. This is awesome. Down is good.
Because that's the green is a pretty strong baseline. As you said, that was like a big, improvement, at least in accuracy and
right.
Very recently.
The fact that we have actually shaved off like 30 steps here, that's a large percentage drop there without really changing accuracy. That's quite nice. Don't believe these runtimes quite yet. That's the right trend, but some of these are run locally and some of them are on AWS, so it's not at all apples to apples. But considering there's fewer steps, you can believe that the runtimes are better. On the downside, the unit tests take longer because they're kind of complicated. But at least the benchmarks might run a bit faster. Not that that's the big takeaway here. The big takeaway is we've shaved off like a third of the amount of time it takes to perform inference, third of the number of steps. We can always optimize the VOCUS code.
Scott, why did you say the unit tests take longer? I missed that.
I don't know, maybe Tristan can speak to it better, but basically it generates, the way we have been writing these unit tests is that it generates a whole ton of example data. And it kind of tries to break your code by just trying to find weird little edge cases. And I think it's quite slow at generating images. Something about it that its internal
Yeah, and so like the new
operational.
unit test for this feature, not as in it's made old unit tests.
Oh, okay,
No,
okay.
no,
Right.
no,
It's not.
yeah,
I think if you have smaller models, everything runs faster. Like, how can anything take longer? But you're saying you have different unit tests, and
And this
yeah.
therefore,
We
is
had quite a few.
right. So the next project is speed up unit tests.
Yeah,
I
yeah,
guess
no, this
one
is
small. I mean,
okay.
this is really exciting and really cool results. But I guess just one small caveat to note on this one is that the gray and the green one are almost doing modality transfer. Like those are on the models trained with the surface agent, whereas the blue ones don't. They are trained with the same agent, with the distant agent. So to really see what's just the effect of the saliency policy, we need to have the green one also trained with a distant agent and then compare that, like dist on dist, to
yeah,
factor out the effect of the modality transfer.
right. So I ran the surface agent on the VOCUS models on this really sparse one and got like 80% accuracy or something like that. It's a pretty big drop, but also it's a big drop in sparsity.
Yeah, that's the
And
modality
big
That's
shit.
transfer in the other direction, I guess. I meant more like running, like for
dist on surf.
taking the green condition and just running it on the models trained with the distant agent, like the dist on dist experiment, just to then see the difference, like how much better is it? Like how many less steps does
Mm,
it take just because it's trained on the same modality versus because it's inferring with the saliency policy?
hmm
Yeah, and I guess the other thing I'm curious, did you have a chance yet to see if you do inference with the VOCUS model, but with the surface ones, surface models, is that also does that also converge faster?
I'll have to get back to you on some of these. I have a whole batch of these things I got to run.
Okay,
I
yeah,
was
no worries, because
I was struggling trying to get some
if it
good.
does, then we could update kind of all our benchmarks at least to use this at inference.
Okay, we've got room to play with in terms of this model sparsity too. Like maybe this sparsity appears to be the best, but it's a bit fluky. If we try to do it on surface models or something like that, or do it in the other direction, maybe this guy would actually end up being the best sparse one. It's always tempting to kind of just do a whole bunch of more parameter scans though, but um, I'm sure we can work something out. At least take a few cracks at it if the results aren't that promising. I am curious to see how the inhibition return alone does, though. Trained and the inference with roughly this amount of sparsity. I'm curious. Okay. Does anybody want to say anything else on this stuff? 'Cause I'm just gonna wrap it up. All right, so these are just a few straggling thoughts. One is inhibition of return by itself drives you to make larger saccades. Um, I'm just reiterating that because we've talked about it before, but I think it has, if you know how learning modules work and what that does to the hypotheses, it really does allow you to eliminate your hypotheses much more quickly. You can prune them out much more quickly. So that's a nice thing just from inhibition of return alone. Secondly, um, these were negative results before I had Ramy's code merged in for the burst sampling. It was basically like this very nice synergy, and it makes, I think it's actually pretty convincing, or I can convince myself. I think I know why it's working with Ramy's code, which is basically uh, burst sampling means you can generate new hypotheses throughout the episode. So you're not so reliant on having a really good first observation. if your sparse model has failed to learn some part of this object, like the back of this hat, then without burst sampling, your initial hypotheses are the ones you got, and maybe they're not that good, and you're kind of just stuck with it. But we're now able to continue to populate the hypothesis space and find better solutions. So thanks, Ramy. And then the other bit here, I just figured we could do any discussion sections on any kind of follow-up stuff or not, if we wanted to move on.
Nice. Yeah, maybe one comment on the kind of follow-up. So yeah, as Vivian alluded to, what we weren't showing with these sparse results is this kind of modality transfer. So these models are really sparse, but they don't necessarily, they're not a good basis for then using the surface agent. Like you said, Scott, you got kind of 80% accuracy. But we have some ideas for what will probably be a future work item. It's not essential to compositionality, so it's probably not something we're going to implement, but something that we can kind of communicate to anyone out there who wants to work on it, is to sort of adapt this salience policy so that during learning, you initially kind of look at the most salient points of the object, or Monty looks at the most salient points of the object, and then slowly kind of loses interest in those. Those become less salient, and it becomes more like this just inhibition of return with a uniform salience. And that would be firstly kind of what you'd imagine you might do if you were looking at an object, that you'd kind of start by focusing on the most salient things. And then if you're continuing to learn about it, you'd start now focusing on the things that may not have been as initially interesting, but are still visible to you. And with that, we should be able to get this kind of best of both worlds, where the salient parts are overrepresented. And so that's what gives us this kind of robustness despite sparsity. But we still have kind of some amount of representation in these other parts of the object, like flat surfaces, so that until we resolve some of the more fundamental issues around enabling sparsity, that yeah, the models can basically be sparse and still give good inference. And then just a quick note on that, maybe especially for everyone on the research team, when we do implement that, we will probably see a drop in performance on the YCB objects. But as long as the models are sparser, that's something we'd be willing to accept, because firstly, we need sparse models. But secondly, we've started kind of saturating YCB, where a lot of the evaluations are getting close to kind of 100% accuracy, which is making it harder to see kind of some of the other benefits. So it's a good time actually to sort of relax these kinds of dense point clouds that we have and move to kind of more plausible models.
Make it a bit harder on ourselves.
Okay. Yeah, sorry, Ramy, what were you going to say?
Well, I was just going to say, I think it's really cool that you're able to push it this far and still get the same accuracy with less number of steps. And I'm just wondering if, I'm always worried with sparser models that we're just not tuning the matching distance and like the max match distance. And I'm wondering if with those models that you pushed, like the VOCUS 4 or the VOCUS 3, I'm wondering if you just try an experiment where you increase the matching distance and see if you still get the same accuracy or better accuracy. It might be.
So
yeah, I could imagine that could help for the surface. Yeah, you mean to basically deal with the fact that we'll be moving out of reference frame or out of model. According to the sparse model.
We will land somewhere, and there will not be any nodes around it, and you just need to increase the matching distance so that you can find those nodes.
Yeah, I can imagine for the VOCUS on VOCUS, sort of by its nature, we're probably landing close enough that it doesn't matter, and hence we get this good accuracy. But maybe that would recover the performance of the surface agent, because that's where it's probably, well, it is almost certainly going into these kind of underrepresented regions and then killing hypotheses that are otherwise valid.
It makes a lot of sense. Yes.
But yeah, but that's a good point that could recover it.
This is my thank you slide. I ran out of time. I would put more people on it, but that's what I got. Thank you, everybody.
Nice.
Nice,
thanks.
nice, thanks, Scott. That was nice.
Yeah, very nice. Really cool project and really cool results.
Thanks. I guess one last thing is that we designed this Salience system to be pretty modular. So when we want to get motion salience and that kind of thing, you can kind of just plug and play different modules when you write them in. So it's definitely something we can extend easily in the future to help deal with things like object behavior and so on. I think pretty trivially, famous last words, but it should be pretty reasonable to extend and play with. Okay, thanks for listening.
Thanks.
Thanks, Scott.